Hi, this is just going to be a quick little aside video from something I found during the testing of the review of this A10 power supply unit. And I thought I'd just make a quick separate video about this rather than include it, somewhere in the middle of this review video. So if you want to check the review of this thing, check it out. Now, what I'm doing is I'm measuring the noise performance, the output noise of this power supply. And the way I'm doing that is I've just got my BNC to banana plug adapter there, my going straight into the scope via a coax, of course, and I've got my scope set up for a bandwidth limit. Now that's quite important because the specs usually of a power supply, let's take a look at it, the ripple here in this case, there it is, 20 hertz to 20 megahertz. So it's a 20 megahertz bandwidth limited range, and that's what the bandwidth limit on your scope does. And if you turn it off, let's have a look at the display at the moment. Okay, that's with the bandwidth limit on. Let's turn it off, and you'll see that the noise is very significantly, peak-to-peak noise there, very significantly higher than if you've got the bandwidth limit down to 20 megahertz. So you definitely want to measure the performance over that limit. But look what we're getting here, okay? This is supposed to be a linear power supply. Quite quiet, okay? Now the spec is 1 millivolt RMS, of course. There it is, 1 millivolt RMS there. Now RMS is the key. It doesn't tell you anything about peak to peak, but you look at this and you go, well, why are we getting this switching effect here? This is not a switching power supply. So where's it coming from? Is it coming from the circuit, the processor inside here? Is it coming like the display refresh or something like that? Is it coming from internal from the power supply? Well, we'll find out in a second. Let's take a look at it. 5 microseconds per division, 3 divisions, that's 66.6 kilohertz or thereabouts. Significant switching, component there. It dominates that display. And if you weren't careful, if you just hooked this up and you didn't know what you were doing, you might think, well, this is coming out of this power supply, and well, this is a shit power supply. Look at this switching, it's horrible, But is it coming from this power supply? You may guess the answer. No, it's not. And let's find out why. Now, the first thing we might check is that what happens when you disconnect it. Okay, you disconnect it, goes away. Not a problem. Let's connect one side of it to it. Not a problem. Connect the other side. Well, we're just getting 50 hertz garbage on there, right? So let's not worry about that too much. But look, you can see the switching component, folks, is still... Oh, I accidentally hit it. Switching component is still in there. There it is there. You can see it. So it's coming, it's definitely coming through this power supply. So you still might think, okay, this power supply is the culprit, but let's switch the output off, okay? So the relay, it should disconnect the output there. So switch all of the outputs off. There we go. Our outputs are physically disconnected. It's switched off and it's disconnected those outputs, but it's still there. You'll notice that the noise really doesn't change much at all, whether or not you got that output on or off. And next up you might think, well, is this BNC, look, is this coax, move it around? Look, it seems to a little bit changing a little bit there. It's sort of, picking up stuff. So I don't know, is it the BNC? Well, let's use a different BNC. So as you can see, the switching is still there, even with this different BNC cable. So it's not that. It's not picking it up. So what do we try next to try and figure out the source of this switching frequency? Because, well, is it the power supply? Because that's the thing, right? If you're doing these sorts of measurements, you have to know exactly where all your noise sources are coming from. And I know for a fact it's not within this power supply, so I'm going to let you try and guess where it's coming from. We're going to try and hunt it down. So what we're going to do now is, well, is there any other lab gear around here, sort of, picking up noise? Maybe this coax ain't that good, right? Is it picking up noise somewhere because it's not shielded all the way in? Maybe it's picking up noise somewhere else. Well, let's try a very simple thing. Let's just switch the power supply off and see what happens. Aha! Look at that, folks. It's still coming through. It's being picked up. What do we do next? Let's pull the mains plug on this thing. Look at that. I just pulled the mains plug and it's still coming through. What do we try next? Well, let's try a real scope probe. You know, I got my 500 megahertz agilent scope probe here, right? It's a real fair dinkum probe. And look, I've even got my antenna earth loop there. And look, we're not picking up anything at all. Now, I'm using my scope probe to connect up to the power supply here, and look, it appears to have gone, but let's stop that. Bingo, it ain't gone. Look, it's still there. There it is, 3 divisions, 1, 2, 3. That's 66.6 kilohertz, still there. So we are getting a better result because this is a much higher quality, proper shielded, oscilloscope probe, as opposed to just, some regular coax, which may not have 100% coverage, but we're still picking it up. So I've gone back to my regular coax here, just so we can see the effect again. And mains cable or no mains cable on this supply, powered up or not powered up, it makes no difference. We're still getting that switching noise. Is this power supply magic? Even when it's not powered, is it magically generating this switching frequency? No, of course not. It's picking it up somewhere. Alright, so I suspect it's a common mode noise being picked up through the mains system, and because this oscilloscope is mains earth referenced, and as you saw in the mysterious oscilloscope phenomenon, you can actually get ESD impulses which jump onto the coax cable, onto the lead, and then because this oscilloscope only has so much common mode rejection from the mains, can actually generate input noise coupled through the earth system. Now, what I've got is this isolation transformer here, and this physically removes the mains earth and isolates this, so it effectively turns this oscilloscope in. It's not mains earth reference anymore, so now you can use your scope probe to probe your circuits so you don't blow them up, etc. But because it physically removes the earth on this thing, it's not recommended to do this. By the way, power your scope. Usually you power your product through this thing and not your scope, or you use a proper high voltage probe. That's for a different video. But look, it's physically changed. Now, it's still there, but it's different. We've got different components picked up. We're still 5 microseconds per division there, but it's not that consistent 66.6 kilohertz we saw before. So, we're getting closer to this thing, and you'll see that it'll instantly go back. If I plug the proper mains cable back into this thing, it'll instantly go back to exactly what we saw before. So we're tracking this thing down. So what we've got is some sort of switching device somewhere, either in the room or on the mains distribution system, that is causing this thing. And just to show you that it's not the agilent oscilloscope doing this, here it is on a Rigol scope, 5 microseconds per division, exactly the same thing happening. So what do? You start looking for things that are either within the direct vicinity that are switching, or something that's connected to the mains system. So you start by, well, I've got my lights up here, my LED lights. I'll switch those off. Does it make a difference? No, nothing. It's not those. Not a problem. Is it the fluoro lights in the lab? Well, only one way to find out. No, look at that. Still exactly the same. And it's none of my gear. I've turned all my gear off on the lab. I've switched the computer off in the office cubicle I've got in here, and I still can't find it. So what is it? Let's go investigate under here. Now, here is all of my power boards. They're all connected down to the one, and there's a whole bunch more powering my electronics bench over there, as opposed to my teardown bench. So these ones here, there's a few things plugged in. Let's have a look. There's what do we got? No, we just got a mains cable that's going off to nothing. Nothing going up to gear that I know is switched off. What is this? What is this? What is this? Hello, Mr. Quee Lee Power. Well, there's only one way to find out. I've now switched this down to 2 millivolts per division. You see we're getting the huge noise there. I'm still measuring the output direct on the power supply, by the way. Well, it's not switched on. There we go. Now it's switched on. There we go. So we're picking up that noise there. What you would think is noise coming from this power supply if you didn't know how to measure things properly. Let's disconnect this stupid Queely. Look at that, switching power supply. Look at it go up as I put it near that coax. Look, bastard. So I'm going to pull the cord on this. I'm just going to yank it. Here we go. Ta-da! We found our culprit, folks. One of these cheap-ass switching power supplies plugged into the same mains board as what I was powering my oscilloscope and my A10 power supply from. Bingo! Big trap for young players. So there you go. We're now at 5 millivolts per division, and you can see that we're still picking up noise, and that is most likely more common mode noise between the earth and the neutral in the mains system, but we've gotten rid of that huge spike which we were getting before that was upsetting our measurements. We can try and track down sources of this type of common mode noise. We can filter our mains and do all sorts of stuff like that to reduce it, but I'm pretty happy now that we've actually gotten rid of that huge 66 kilohertz spike we were getting from that switching power supply. And of course, if we go back to our original issue and just disconnect it from there, bingo, we're no more noise, and we can even go down to 500 microvolts, you know, per division, and we're sweet there. Why is that not updating? Bloody firmware in this thing. I haven't got the latest firmware for this Rigol scope yet, so it has some freezing issues with the horizontal mode, but there you go, that's 500 microvolts per division. Switch that and put that in, we pick up a bit more, we put it over on our power supply over here, and we're going to pick up a buttload of common mode noise. But that's not coming from our power supply. So you might be asking, well, why was this thing picking it up even though it's switched off and disconnected from the mains like that? Well, it's because the internal circuitry and the internal transformer in here is effectively, via AC coupling, is effectively working as a very effective pick-up antenna, so to speak. And that's why this oscilloscope probe won't pick it up, because this is a relatively high frequency pickup coil, okay? It's going to pick up, ESD and lots of high frequency discharges and stuff like that, as I've shown in previous videos. So the transformer inside here and the coupling to it is basically going to effectively work as a better lower frequency pickup antenna for that stuff. That's why if we disconnect it, bingo, we're gone, okay? But we hook it up, this thing's entirely switched off, disconnected from the mains plug, so it's not actually picking it up through the mains earth. It's still working as a very effective antenna for picking up that common mode noise. And common mode noise comes in all types, folks. It can come from anywhere. Be careful, watch this. I'm going to grab this coax with one hand, touch this screen over here. No, folks, it ain't magic. It's picking up the noise, the switching, that refresh of the screen there. Look at that. Woohoo! And of course, that is one of the claimed, it is one of the disadvantages of these digital scopes, is that they can be spewing out stuff which can interfere with low value measurements. So that's why, a lot of the greybeards frown upon these digital scopes, because they can, be generating all sorts of crap. You won't get this sort of thing happening with an analog scope. So what are we going to do when measuring our A10 power supply here? We know it's a linear supply. It's not spewing out any switching stuff. So all this high frequency peaks in here are common mode noise coming from somewhere else in our measurement system. So when we're measuring the noise on a linear power supply like this A10 power supply, we know that these high frequency switching components in here are effectively common mode noise being picked up somewhere else in the system. So really you want to chop those out and only look at that in there. So as you can see, even though we got rid of that main source, we're still picking up, you know, a lot of common mode noise in here, and unfortunately that's going to be hard to get rid of. Now, even if I power both the scope and the power supply through a filter, a mains input filter board, so I've got both bits of gear, that's the only thing off that filter, we're still picking up this pain in the ass common mode noise here. Look at that. So what's that coming from? Well, we go full circle back to something that we tested before. Our lights. Let's turn it off. Look at that, folks. Bingo. So now we're talking. We've started to eliminate all of our problems here and getting towards more of the real noise performance of this power supply. So really, we still have, that's me, by the way, be careful, there you go. So that's, we're getting very, very close. There's still still a burst in there that's triggering off that. So it's obviously, we can move our trigger around, and there we go. We can single shot capture off that. So there is another burst event coming in there, but really, that, folks, now we can at least get a more decent measurement of our power supply. You can see how this is not easy. We originally had a common mode noise source directly, a switching power supply directly on there. We thought we eliminated the lights, but we didn't. Let's switch those lights back on. Look at that. Unbelievable. Woohoo! They're the LED lights I've got up the top, and they're not even supposed to be PWM, and they're supposed to be constantly on at maximum brightness there. I can turn my other set of LED lights above, does absolutely nothing, but those lights I've got up there, big switching noise. So we came full circle there, and we're getting closer to eliminating everything. So let's actually look at the differences in the quality of some coaxes. I've got this particular coax cable here. We're 2 millivolts per division. I'll keep it on that. And that, you can see, we're picking up lots of high frequency common mode noise there. Now you'll see that the bulk of the ripple and noise in there is going to pretty much stay consistent between these. Now let me try another coax cable here. It's roughly the same length, but it's going to be a different type with a different outer weave. So here's this other one, and you can see that it is particularly cleaner. I mean, if we put it near the screen there we go. That's why the other one was picking up so much crap. The weave wasn't as good, the shield wasn't as good, and it's picking up more of that stuff from the screen. Now, if we disconnect that and we plug in our scope probe, our proper scope probe, this is the 350 megahertz one which comes with a Rigol, and it's got a ×1 ×10 switch, so we'll put it on ×1, so it's operating just like a regular coax, and I've got this little coax adapter. It's a bit loose, so please forgive me if the connection is a bit intermittent there. I may have to hold it. There you go. Look at that. We're suddenly, with this good quality, properly shielded, high bandwidth oscilloscope probe, look, it's not picking up nearly as much. So our performance has gone from, pretty, sort of fairly ordinary. We're still at the same volts per division, 2 millivolts per division, but much cleaner with the scope probe. Now let's put it on ×10, and then we have to compensate. We've got to go in here, and we've got to turn that to ×10, and then we're on 20 millivolts per division. We've got to, we can't actually go down to 2 millivolts per division because we have to be 5 millivolts per division, and it's higher. Why is the noise higher on ×10? Well, it's because a ×10 oscilloscope probe is higher bandwidth than it is on ×1. And if you don't believe me, here's the spec sheet for it. There it is, bandwidth ×1 DC to 8 megahertz, ×10 DC to 350 megahertz. This is the spec sheet for this Rigol probe, and all probes are the same. That's why a lot of them only come ×10, because they give you the high bandwidth. It's due to the input capacitance. I won't go into it, that's a whole separate video, but ×10 probes, that's why they're used, is because they are higher bandwidth. So effectively, we've gone from that 20 meg filtering on our scope to an 8 megahertz bandwidth filtering, and that's why our ×1 probe is actually going to give us a lower noise measurement because it's bandwidth limited. So all that high frequency noise, wherever it's coming from, is being attenuated. So really, because the bandwidth of this power supply is specified from 0 to 20 megahertz, we can't just use our scope probe on ×1, because that's only giving us, for this probe, only giving us an 8 megahertz bandwidth. So we have to put up with the fact that we're using a ×10 probe, and here's a agilent one. This is my 500 megahertz high quality agilent probe, and that is we can only go down to 5 millivolts per division because of the ×10, but there you go. That, folks, you still get the occasional high frequency glitch in there. You might be able to see. In fact, we can probably even trigger off that. And there we go. Yep, we can actually trigger off that. It's the occasional little high frequency pulse switches coming through, but not a big deal. So there you go. Now we can measure our noise with reasonable performance. Excellent. So there you go. I hope you found that interesting. That just goes to show that there's more to a simple noise measurement than meets the eye. Common mode noise, go look it up, go research it. It can be a real pain in the ass and a big trap for young and old players alike, let me tell you. So if you like that, please give it a big thumbs up, and if you want to discuss it, jump on over to the EEVblog forum. Catch you next time.